Okay, so I think I'll start with Newman projections and then we'll go into chair conformations because Newman projections is what I saw that most people were struggling with. So, yeah. So the main thing with Newman projections is just making sure you put everything in the right place. And so for Newman projections, it's pretty much, let me try, the circle and then two things coming off of it. And this will be the back carbon. Okay, yeah. And then the back carbon, which will have stuff coming from it. And then the front carbon, which would be just drawn like this. So let me just do a basic example so it can make a bit more sense. And then I'll explain more in depth on how you know where everything goes. Okay, so for this molecule, okay. So for this molecule, it's not too complex or anything, but as you should have been taught, wedges are coming towards you and dashes are going away, and these are the little dashes that I made here. And these are the, yes, these are the wedges. And so what I use that really helps me is knowing that dash things go to the left and wedges go to the right, which really that really helps with knowing where things go. And I will just write that so we know. Okay, so for this, when you're looking at it, what my professor said, like to make it like much more simpler, was to imagine that you have a little person at whichever viewpoint and you're basically walking in. So let's pretend the little person is right here and they're looking in this way. So that's how you know which one is the first and second carbon in the front and back carbon. And so for this one, this will be our first carbon and our second carbon. So for the first carbon, it'll go on this front formation right here, this one. And so when it's just a straight line, like we have with that's holding the CH3, it'll either go up or down. So for this first carbon, it'll go here. And then since we have this H that's dashed, it'll be going to the left. And then we have the nitrogen with 2 methyl groups on a dashed, so it'll go to the right. No, on a wedge, so it'll go to the right. And you'll do the same thing for this carbon. The bromine is on a dash, so it'll go to the left. Wait, no, it's on a wedge. My bad. It's on a wedge, so it'll go to the right. And remember, the circle holds the back carbon, so you'll put it on that. And then the straight line has the CH3. And the H is the dash, which goes on the left. So that's pretty much it. And when it comes to finding the most stable conformation when it comes to Newman projections, you have to make sure you see the 2 biggest groups. And once you find the 2 biggest groups, you will make sure they're the most farthest apart that they can be. So the 2 biggest groups that we have here are the nitrogen holding group, and then, oh, you look for the 2 biggest groups on each of the carbons. Yes. So then on the back carbon, it's the CH3. So right now, as you're looking at them, they are not really that stable because, you know, both of the biggest groups are right next to each other. So in order to stabilize it, you keep one of the carbons the same. So I usually keep the back carbon the same. So it'll be, so you'll keep it the same here. And then you'll make sure the nitrogen will be right across from it. So when you draw it here, the nitrogen will go here. And notice I'm just rotating it this way, so it'll push everything that way. So the hydrogen will go where the nitrogen used to be. And the CH3 will go right here. And yeah, that's how you do the most stable. And that is really necessary for when you're looking, when you're ranking and when you're looking at other molecules and making sure that you're drawing the correct. So yeah, do you have any questions so far? Okay, good. Okay, so let's go on to chair structures. And with these two, chair structures are pretty much similar in a way, but like not exactly. But when you're looking at stability, you want to make sure that they're not, that the 2 biggest groups are not close to each other, or they're both on a wedge or a dash next to each other. So let me look for an example of chair conformation so we can go over. Okay. So, for example, this molecule that we have here, when it comes to chair conformations, you want to make sure that none of the biggest groups are not like this, and they're not like being held like at the same point, like they're not on a wedge or a dash or close, because then you get basically hindrance here, and it's not good for the molecule overall. So yes, working through this, you can tell that A obviously isn't correct because those two big groups are basically right across from each other in a 1-3 conformation. You don't want that. That's really bad. So then you go on to B, and this is much better because the bigger groups are farther from each other. And then, but it's not quite because they're both still like both on, hold on. Yes. So when it's like that, they're both dashed. So when it's coming up like this, they're both on a wedge. But here in B, they're both dashed, and you don't want that. You want one on a dash, one on a wedge. So that's what we have here. And we have this one on a wedge and this one on a dash. Yes, on a dash. And then we also have that here again with this one on a wedge and this one on a dash. And so then it's really between C and D. And so which one do you think it would be?
I'm thinking D because they're farther. Or
Yeah.
wait, actually, wait, hold on. Um, actually, I'm not sure.
You're close. It's you're right about it being farther, but oh wait, no, actually you're right because with all the in C, all the hydrogens create like a lot of steric here. So it would on C, so it wouldn't be correct. So D's correct. You got it. So yeah.
Wait, could you re-explain the hydrogens being really close together on C versus D?
Okay, so on C, the hydrogen here is on a wedge, and these three hydrogens here are on a wedge, and then this one here is on a dash. And so imagine this is a carbon, and so there will be three hydrogens here, and then this one obviously here, and this one here. And it's just a lot of molecules on that side, so you really don't want that. So having this group here, the three here, and this one like down, which is like farther away, is much better for the molecule than this here. Do you get it, or should I try and explain it
I'm
in a
probably gonna
bit?
need another example on this. I'm trying to
Okay,
absorb the whole
it's
hydrogen space thing. Yeah.
it's fine. Let's move on to another one.
Oh wait, so for that one, because it tells us the chirality, could I check the chirality then around those carbons to pick the one that's more stable? Or for this one, yeah, I guess we could check the chirality, right? To figure out which would be the most stable.
You could, but it's typically easier just to like just to I when you do more practice problems, you kind of like get it. It's kind of a bit like tricky for me to explain here, but like you just don't want too many molecules. Point. Can you see my little pointer?
Mhm.
Yeah.
Yeah.
So you don't want too many molecules here because it's just not stable most together. But when you have it in this way, with the hydrogen in this position instead of this with the CH3 in this position rather than in this position, it's just better for the molecule.
Yeah, maybe it is a practice problem thing, but yeah. I know I'm not really quite getting it right now, but maybe once I keep seeing it.
Yes.
Okay.
Okay, let's try another one. But the thing about chairs is that um as long as the in the 1-3 position that you don't have both on a dash or both on a wedge, then that's the main thing that you really need to know, because typically you won't have questions like that, but it'll mostly be between if it's on a wedge or if it's on a dash. And if they're both on a wedge or both on a dash, you don't want that. And
Mm-hmm.
you so yeah. So let me look for one more problem so we can work through
If
that.
you want, I could. Wait, is there a way I could share? Wait, hold on. I can pull up the question that I had for ranking those chairs if you
Okay,
want.
yeah.
Okay.
Yeah, let me see. I think you should be able to share now.
Okay, cool. Let me just. Okay, so I mean, this one's not the ranking one, but this one's identify lowest chair conformation. So lowest energy, I know would mean most stable for this. Okay.
So yeah, we can work through this one. So okay, I
Yeah.
don't know if I can draw, but let's work through it together.
Mhm.
So let's start by eliminating which ones it could and could not be.
So I
So
think that my biggest, like, this is my main concern, right? About where that goes. I think that's the orientation I'm most concerned about. But otherwise, I think for me, I eliminated this one because they're really close together. And yeah, for sure, definitely I eliminate D, just because those hydroxides are super close together.
And if you notice, like D, C is also they're also really close because they're both on a wedge. So you could also eliminate C because you don't want that hindrance right there. You never want that 1-3 hindrance. So that's also bad. So you can eliminate that one.
Both on a wedge, so going up, right, on the axis?
Yeah.
Okay.
I know it's kind of tricky to see like whether it's on a wedge or a dash in the chair, but you'll get the hang of it. Okay, so then it's left between these four. So for
Because I know during the test for this one, like I flipped a lot of them in my head to see can this pair still kind of balance. I don't even know if that was effective, but yeah.
This one's actually tricky. I don't think I had one this tricky on my exam.
Let me check on this one. I don't remember if it was B or C. How do I do this? Oh, mouse. Wait.
Yeah, because I was thinking it would either be B or F.
It says E. Okay, so it's E. Okay, so we eliminated the right one so far. That's good to know.
Okay.
Yeah.
So, yeah, E. Okay, I can see why they said E. So here you see the OH on the left and on the right. They're the farthest that they can be. So they're not hindering each other. And E is basically has its own space because none of them are on a wedge near it. So yeah, I think that one. But when it comes to eliminating the rest, I can see how that's a bit tricky. But wait, on F, both of them are a bit closer, so I can see why that one's less stable than that. And
I guess
B, I could see how someone could pick B, because, but yeah. But E overall is the best one, obviously, since that's the correct answer. But yeah, it takes time to really know how to do this. But typically, whichever molecule has them farthest apart is overall the best.
Okay, really quick. Also for wait, let me just circle this for myself. So for like A and versus B, this orientation, I know this is axis or axial, but this one you said would be going up, right? Or so it would be a wedge or no, a dash?
Yes, it would be a dash. Wait, for A or B?
For A on the hydroxide on the left.
For A, that would be...
Because the angles, I noticed some of these are really angular when it's in these chair conformations, and I'm not sure how to read some of those unless it's super clear.
Yeah, I get that. Typically, if it's going away like that, it's a dash. But if it's going up, then it's a wedge. But I can see where it's like here on A, because on A in my notes, what my professor told me was that this would be on a dash. So just knowing the difference can be tricky, but
yeah, that part helps more about the whole going up. It's presumably on a dash versus going down or angling down. As we can see here on F, the angle's down. You know.
Yeah, typically that's how it should go. Yeah, so do you have any other questions that you would like to go over?
I mean, I think chair is really my main concern for me, so I can better understand the concept and then do problems and understand those problems instead of just blindly doing problems. But I'm trying to take some notes before doing those problems now instead of learning while doing the problems like I did before. And it was like,
Yeah.
it's fun, but you're really sabotaging yourself and wasting time. So
Yes. And using the textbook, especially since you go to UTD as well, is really helpful because they have a lot of problems that you can use in that. And if you would like me to share some additional problems with you, I can too, because I have a lot of extra problems.
yeah, absolutely. That sounds great.
Great. So I think I want to do one ranking of Newman structures just because I discussed it in this session, and then I'll just wrap it up. I think I have a few more minutes. So
Yeah, sounds good.
okay. So when it comes to Newman projections, like we were talking about in chair conformations, the the goal is to make sure you have the biggest groups the farthest away. So our big group on the first carbon is this one, and our big group on the back carbon is this one. So automatically we can see that this structure here is one of the not as stable molecules. And here we see this. Although the groups are farther apart, um, because it's eclipsed, it's less stable than it would be if it was staggered. And staggered is just a normal conformation, normal position like this one. So yeah, so this one is less. And then we see this molecule, they're both next to each other again, but they're staggered. And this one, they are together, they are farther apart, but they're eclipsed. And this one, they are the farthest apart. So we know that this one is the most stable. And then automatically,
Wait, for the
um,
fourth one,
mhm.
is this the back C? I think you circled the wrong CH3 for the
Oh,
back.
yes.
Yeah, that's all. Okay. Yeah, but I agree with the last one being the most stable because the big groups on the back and the front are farthest away from each other.
Yes. Thank you for catching that. Yeah, so next, when you're looking at which one's most stable, you look at the ones that are next to it but not eclipsed. So we can look at so this first one and this third one would be the next two for us to look at. And when deciding which one is more stable and less stable, you'll look at the other big groups on the molecule, and you see this big group and this CH3. And as you can see on this one, they're all right next to each other on the first one, and they are a bit farther apart on the third one. So it would be this one would be the third one would be the second most stable, and the first one would be the third most stable. And for this one, for the second one, you would see that it's the fourth most, and that would be because the big groups are more farther apart. And yeah, they're more farther apart. And on this one, they're right next to each other, which is the worst situation that you could have. And you definitely don't want that. So this would be the fifth one. So, do you have any questions? Okay. So I think that wraps up our session for today. And thank you for attending, and hope you have a nice weekend.
Thank you.
You're welcome.
Do you try to host these weekly or like every other week or something like that? I was just curious. Or do you just go by demand?
I was going by demand before, but most people want more sessions now, so I will be doing them weekly.
All right, sounds good. Okay, thank you.
You're welcome. Bye.